Hello, my name is Giorgio Morales. I'm a PhD student in computer science at Montana State University, and I'm going to present our paper, Two-Dimensional Deep Regression for Early Yield Prediction of Winter Wheat. To begin, we know that we're living in this precision agriculture era in which we have access to a lot of information. We have new satellites, new sensors, and machines that allow us to process all this information efficiently. These tools are used to elaborate strategies to make efficient use of the available farming resources, such as water, herbicides, fertilizers, and so on. But before reaching that point, we need to develop models that relate input factors, such as the environmental conditions, and outcome variables, such as the crop yield, or in other cases, protein content. To develop these models, we use on-farm precision experimentation, which generates site-specific data on responses to field management. In this work, we're going to focus on the crop yield prediction problem, which is one of the main tasks in precision ag. This problem can be automated based on multi-source periodic observations of the fields, and that means that for a given field, we can collect data from previous years and train a model that tries to understand the behavior of this specific field under different conditions. Then when we have new information from the last observed year, we simply apply the trained model to predict what is going to be the yield during the harvest season. These models provide the farmers with tools to make informed decisions. So, for example, if we identify a specific region that is not going to produce enough during the harvest season according to our predictions, we may want to take some actions, such as increasing the nitrogen rate applied on those regions. And that is an optimization problem that requires more analysis. But of course, the first step is to be able to predict the yield accurately. There are many related works in this area, and most of them use classic machine learning approaches, such as linear regression models, support vector machine regressors, or random forest. But due to the boom of deep learning in the last few years, we've seen that there are new approaches that use deep neural networks or convolutional neural networks. So for example, Perlink et al. In 2018 used a deep neural network and a stacked autoencoder with spatially sampled data for yield prediction. And that means that for each specific geographic point of our field, we're going to use its information and also the information from the surrounding points to predict the yield value of that specific point. Perlink et al. In 2019 proposed to use two versions of the AdaBoost algorithm, namely AdaBoost R2 and AdaBoost R delta, using feed-forward neural networks as weak learners. She also proposed a novel AdaBoost algorithm called approximation AdaBoost that uses the loss function of the AdaBoost R2 method, but uses the threshold approach of AdaBoost R delta to calculate the probabilities and the weights of each learner. She showed that this approach gives better results than if we use a single network. Now, there are other approaches that use convolutional neural networks because they are a natural way to exploit the spatial information. And for instance, Yu et al. In 2017 proposed to use convolutional neural networks and learn short-term memories for learning spatial temporal features. And that is because they are collecting data from different stages of the entire growing season. Russello et al. In 2018 focused on the same type of problem, and he proposed to use three-dimensional convolutional neural networks. And he showed that this approach yields better results than those obtained by Yu et al. And finally, Barbosa et al. In 2020 proposed a multi-stream CNN architecture called CNN late fusion. And each stream of this architecture is a small CNN that analyzes each feature separately. And at the end, we're going to fuse all the features using a single neuron that is going to give us a single yield predicted value. Now we're going to tackle the crop yield prediction problem using a deep learning approach. And we have two main contributions in this work. First, we're proposing a CNN architecture that we called Hybrid 3DNet Reg. This is based on a network that we proposed on a previous work called Hybrid 3DNet. This network is used as a two-dimensional regression model for yield prediction. And it is two-dimensional because the output of our network is two-dimensional as well. So if I'm using a CNN, my input is two-dimensional. It is a patch or a square that represents a neighborhood within the field. We process this information through the CNN, and the output is going to be two-dimensional as well. And it can have the same dimensions as my input, as we will see later. And each pixel represents the predicted yield of the corresponding input pixel. We will show that using this approach of having two-dimensional outputs yields better results than other 5 methods that we use for comparison and that we introduced in the previous slide, namely approximation data boost, a stacked autoencoder, a three-dimensional CNN architecture, a CNN late fusion architecture, and we're also including multiple linear regression. Note that these methods may use a one-dimensional or a two-dimensional input, but the output is always a single yield prediction value. Now let's talk about the data sets that we're using in this work. We are collecting data from winter wheat fields during the early stage of the growing season, which corresponds to March. And using this data, we train models to predict the yield values during the harvest season, which corresponds to August for the winter wheat. Now, this approach is a little bit different to many of the works that are out there because we're not using information of the entire growing season. It turns out that the farmers take decisions in March, such as deciding the amount of nitrogen they are going to put at different parts or regions of the field. And we cannot wait until May or June to have more complete information. We need to use what we have available until that moment. And we are using different types of data, such as images from the Sentinel-1 satellites. And these are radar satellites. So the main advantage is that the cloud occlusion is not a problem because the signal can go through the clouds and return in the same way. And we are using 2 radar images with different polarization. They are called vertical and vertical horizontal. We also have on-ground data. And we have the nitrogen rate applied at different regions of the field, the precipitation, the slope of the terrain, the elevation, topographic position index, and the aspect of the terrain as well. And this is how a real yield map looks like. We are aggregating the data such that each pixel in this raster or image corresponds to an area of 10 by 10 meters. And this is how we are creating our training datasets. We decided that the inputs of our CNNs is going to be a patch of 5 by 5 pixels. So here we're automatically extracting 5 by 5 patches, allowing overlapping between them to obtain more training samples. And there are regions that are not being covered by the patches because they contain missing information, and we're avoiding that. We are using 4 fields from farmers from Montana. And the data collected from previous years is used to create our training and validation sets. And we're going to reserve the information from the last observed year to generate entire yield maps so that we can compare them to the real or to the ground truth yield maps. And also we will compare them to those obtained by the other methods. So now let's see how the yield prediction models work. As I mentioned before, the input is a patch of 5 by 5 pixels, but we have 8 features among on-ground data and remotely sensed data. So the input is a concatenation of 8 patches of 5 by 5 pixels. So this is an input data cube that is going to be processed by our CNN. And the output is a 2-dimensional patch that in this case has the same dimensions of the input. So we say that the output window size is equal to 5. Here, we are predicting the yield values of all the pixels that appear in the input simultaneously. So, for example, this pixel represents the yield value of the region of the field that is represented by this pixel here. It is also possible to have smaller output window sizes, like in this case, we consider n equals 3, and the output is smaller. It represents the yield values of this region within the dotted square. And finally, we can also predict a single value as the other methods do. And this value represents the predicted yield of this center pixel. And this is our general Hyper-3 net reg architecture. As you can see, the input has these dimensions. This one means that the input is considered as a single data cube with dimensions 5 by 5 by lowercase n that denotes the number of features in our problem, which is 8 in our case. Then we have these two major components. The first one is called a 3D feature structure because it is structuring features using 3D convolutional blocks. Then we have our 2D encoder that uses 2D separable convolutions and progressively reduces the number of feature channels. Finally, we have a normal 2D convolutional block whose objective is to reduce the number of channels from 32 to just 1, because this is our final yield prediction patch with an output window size of n. So if we want an output size of 5, we need to apply padding because that allows us to maintain the size of the feature map with respect to the input feature map, considering that we are using a kernel size of 3. And that is what we've been applying through the network to maintain these dimensions of 5 by 5. But if we want an output size of 3, then we don't apply padding and the feature map is reduced to 3 by 3 by 1. And finally, if we want a single output value, we use this previous convolution layer. The output is 3 by 3 by 1. We reshape it into a vector of 9 elements, and then we apply the fully connected layer, which is basically a neuron with 9 inputs and just 1 output. And I have an example here that will help us to visualize the architecture of the network. This first component is the 3D feature structure. It is actually a densely connected block that is concatenating the features that come from each layer of the block. Then we reshape it into a 2D tensor or feature map, and we are applying our 2D encoder that is progressively reducing the number of channels from 512 to only 32. And finally, in this case, we want an output window size of 5. We are reducing this feature map into a single patch of 5 by 5 by 1 with our yield prediction values. The last step is that after training a model, we need to actually use it on the test set that corresponds to the last year of observed data to generate entire yield maps. And we do that by using a sliding window of 5 by 5 pixels. So we move this window horizontally and vertically through the field so that for each point within the field, we apply the trained model and we generate a yield patch. The issue is that neighboring pixels have overlapping yield patches. And that means that for each point of the field, we probably have more than one yield estimation. And we reduce it to a single value by averaging these different estimations. And here we have an example. We have the point ij that has 2 horizontal neighbors and 2 vertical neighbors. We generate a yield patch for each of them of 3 by 3 pixels. And we want to combine information of all these 5 patches to generate a single yield map. And we do that by averaging overlapping regions. This upper left pixel is special because it does not overlap with any other patch. So we don't need to do anything with it. But here we do because this pixel comes from the intersection of the patch A and B. So we average 2 values. This pixel is special because it comes from the intersection of 5 different patches. So we need to average these 5 different values. And that is telling us that we have 5 different yield estimations about the same region of the field, about the same pixel that were calculated using different inputs. So the more samples we have about a variable, the less uncertain is the result. And that is what we want in our case. And for future work, we're going to use a distance-weighted average to combine information of all these pixels. This weight is going to depend on the distance that a given pixel is from the center of the yield patch that it comes from. And here we have an example of the type of results that we obtain using our method. First, we have the ground truth yield map, which is the real yield map that was collected in August of 2020. We also have information about this field from previous years, from 2016 and 2018. And using that data, we train a geoprediction model. And then in March of 2020, we collected information about this field and we applied the train model using the methodology that we explained in the previous slide to generate this predicted geomap. As you can see, there are regions of high predicted yield and low predicted yield that coincide with the actual geomap. And even these smooth changes in the lower part of the field coincide. And here we have an error map that is showing the square error between the predicted geomap and the ground truth geomap. And we're also reporting the root mean square error for this field, which is 15. And finally, we have this structure similarity map, which is calculated using a window size of 11. So the yellow pixels are telling us in which regions our predicted geomap is more similar to the ground truth geomap. This metric is between -1 and 1, and here we're reporting the average score for the entire field. Now let's compare the results that we obtain using our method with an output window size of 5, 3, and 1. We will compare it to other 5 geoprediction methods, and we have a approximate AdaBoost, the stacked autoencoder, a 3-dimensional CNN architecture, a CNN late fusion architecture, and a multiple linear regression model. And we're including this one because even though it's very simple, it gives pretty accurate results sometimes. So for each field, we're going to report the root mean square error, the root median square error, the average structural similarity using a window size of 3, and also using a window size of 11. And we're putting the star here because we're multiplying the original metric by 100, so that's easier to see the differences. We notice that we obtain the best results when we use an output window size of 5 for almost all of the cases, except for 2 cases here. So for example, for the Henry's field, we obtain an RMSE value of 10.88, whereas that obtained by the CNN late fusion is 10.73. But we have to take into account that we don't only want to reduce the overall error, we also want to generate geomaps that are similar to the actual or to the ground truth geomaps. And that is why we need to take into account the similarity metrics. So we obtain one of the lowest RMSE, but also the highest similarity metric. And that is why these results are the best. And we will be able to see that visually in the next slide. So here we have the ground truth geomap for the Henry's field. And here we have the result that we obtained using hybrid 3D net reg using an output window size of 5, 3, and 1. And we can see that we obtain the generated geomap that is most similar to the ground truth in comparison to the other methods. We also need to note that if we reduce the output window size from 5 to 3, we are going to obtain noisier results. And the same is going to happen if we reduce the size from 3 to 1. And that is because in this case, we have more estimations per pixel or per point so that we can provide more confident results. For this field, we obtain the lowest RMSE value, but we also notice that our method is the only one that is able to predict this complex behavior in the lower part of the field, which is something that the other methods can't do. And finally, for this field, we only had 1 year for training our models, and that is why some of these methods present overfitting problems. But in spite of that, our method is the one that presents the most robust results. So we are tackling the crop yield prediction problem as a 2-dimensional regression task. And that means that we're predicting 2-dimensional yield patches. The experimental results show that our Hyper 3D Net Reg architecture, when it uses an output window size of 5, generates the most accurate predicted geomaps in comparison to the other 5 geoprediction methods that use a single output. We also show that when we use an output window size of 5, we obtain better results than when we use an output window size of 3, which in turn It's better than when we use a single output. So for future work, we're going to modify our networks, and instead of having just one single output with the geoprediction value, we're going to have three outputs, where the two extra outputs represent the lower bound and the upper bound of the prediction. And the objective is to provide narrow and accurate prediction intervals so that we offer a degree of confidence alongside each prediction. We're also going to propose a saliency analysis for our models so that we will be able to identify the most or the least nitrogen responsive regions within the field. So with that, I would like to thank you for your attention, and I'm looking forward to hearing your questions.